Okay, so let's get back. So this is the Taylor series expansion. So you can write any function, any continuous function as a function of. Yes, the session is being recorded. So I'll upload the link. I think the NPTEL course coordinators will share it with you guys. Yeah, for that only I was having some issue recording. Okay, so the main thing is the Taylor series expansion. So Taylor series expansion, this is any function at any point. For example, if you have a point here a point here which is delta x apart from here. So you have some value a and you want to find what is the value of a plus delta x, right? So you can find it using the value of a and its derivatives along x direction. Okay, so what it looks like, it looks something like this. Will be phi a plus, this will not be dou, this will be dx by delta x 1 factorial d square phi dx square delta x square by 2 factorial and so on. Okay, so what is the format of this expansion? So in general we can write phi of a plus delta x is nothing but a summation of I is equal to 0 to infinite uh, to di dxi delta x to the power I divided by I factorial. Okay, so this is how the Taylor expansion looks like when you have a single variable. When the function is varying with a single variable, here example x. Okay, okay, I'm really sorry. Please feel free to unmute yourself and uh, tell me if something is wrong. There is no issue. Okay, please feel free to unmute. Okay, let me just do it once again. So I just started with the Taylor series expansion. So what it does is that, for example, you have a function, you have a continuous function phi, which is a function of x. Okay, which is a function of x, and somebody wants to join, I think. Okay, so this phi, for example, is a function of x, and we have, for example, at x equal to a, we have a value of phi which is phi a. But now we want to find the value of phi at a distance of x is equal to a plus delta x. Okay, so what Taylor series expansion allows us to do is that when we know the function phi at a, we can also get the value of phi of a plus delta x using this sort of an expansion. I'm really sorry for the interruption. This is my first time. I hopefully in the next tutorial I'll be much more much more habituated to it. I'll again streamline this process. Okay, so phi at x is equal to a plus delta x, we will write it like this. Okay, so phi do d phi dx at point a times delta x plus d square phi dx square at a delta x square by 2 factorial, here also 1 factorial is there, plus d cube and so on, right? So in general form we can write something like this: at a plus delta x we can write a summation of I from 0 to infinite di phi dx I delta x to the power I by I factorial. Okay, but in general, if you looked at sir's lectures, you saw that we only take the first two terms, right? these terms these terms these terms become so small that these are generally neglected. So you might wonder why these terms are neglected, because if you see that as we go ahead in this series, this delta x, it gets multiplied. Okay, it gets squared, then cube to the power 4. So if your delta x is very small, then all these terms will become negligible. You understand, right? So for example, if your delta x is 0.1, your delta x square will become 0.01, then delta x cube will become 0.001. So these things are, so what we can say is that is delta x square is very less than delta x, and similarly delta x cube is very less than delta x, and so on, right? So this is the reason. So in what we do is that we generally neglect the terms. We are only considering the first two terms when we derive the equations. Okay, so I will give a brief overview of the conservation of mass. So in if you remember the in so in CFD, or when we solve for fluid dynamics equations, we generally solve for the conservation of mass, momentum, and the energy. Energy can be either in the form of internal energy or enthalpy or whatever other form. There are a lot of forms of energy that you can use. Okay, so all these things together is called the Navier-Stokes equations, and these are all very non-linear, and no closed form solutions. So as a result, what happens is that when we do not get a solution for fluid flow problems, because yeah, yes, we do not get any solution of these fluid flow problems based on pen and paper calculations. Okay, for example, if you see some kind of differential equation, for example dx dt is equal to x ax or a minus x, what will you can easily find the solution, right? So how x is varying with t, you want an x to be a function of t, right? And this is quite straightforward, that you can find the solution of this using basic integration. So here dx by x is equal to dt times a. So this will, if we integrate 0 to x, 0 to t, it will be nothing but ln x is equal to at, and x will be nothing but e to the power at. Okay, so at any time, so if you have t at any time, for example 0.01, we can directly get the value of t at 0.01 using this e to the power a times 0.01. So a will be, say, example 5. So we can get some value, for example 5.3 or something like that at any time. For example, t is equal to 1, t is equal to 100, t is equal to 1000, anything is possible. But what happens to the partial differential equations that we get from the conservation of mass, momentum and energy? We are not able to solve these equations analytically, and as a result, what do we have to do? We have to rely on the numerical methods, and numerically we have to solve these equations. So we generally solve this equation using computers. For example, in my research, I solve for the whole Navier-Stokes compressible Navier-Stokes equation, along with the species transport equation, which dictates how the different multi-component mixture is behaving in combustible flows. So we use numerical solvers where we provide initial conditions. So these solvers we solve using numerical solvers. So if for these solvers we need to input the initial condition, the boundary condition, and then we give, there are a lot of parameters that we can assign to the numerical methods that we solve. We can choose appropriate numerical methods. We can choose appropriate grids, then we finally get the solution that we need. Okay, so these things as initial conditions and boundary conditions, you do not need to worry about these things. Sir will again touch upon them, and these numerical methods, the type of grid and all, these will come in at a later stage. But now what we will focus on is grasping the fundamentals of CFD. By fundamentals, I mean what are the governing equations, and how to derive them from first principle. And later on, we will see that how do we solve for these partial differential equations that we derive. Okay. So till now, anyone has any questions? Questions regarding this part that I touched upon, or any other questions regarding how the tutorials will go, what will be the format and all. So since this is the first tutorial, I also want to take your opinion on how do you want to use these tutorial sessions. So anyone have any questions or suggestions for me? Okay, seems everyone is okay with the way I'm going. So even if I am going a little bit fast or slow, you can unmute yourself at any time and get back to me. Okay. Okay. So let's start with the conservation of mass. Okay, we will straight away go to a build a 3D domain and see how things play out. We will use the Taylor series expansion also. So this type of control volume, this is the control volume, which is the principal part of the finite volume method that sir will be teaching you. So there are multiple methods to solve these equations, right? There is something called finite element method. There is something called finite difference method. Okay, so these things are different ways of solving these governing equations. But all these equations generally are derived from a control volume approximation. Okay, so we assume that there is a control volume in the fluid which with which we are interested in. Okay, we do not consider individual fluid particles or molecules that are inside, but we assume this to be a continuum. By continuum, what do we mean? By continuum, we mean that, for example, the dimension is delta x, or let's stick to the convention delta x, and for example, each molecule has a mean free path. Okay, if you remember, so for example, this is a molecule, and each molecule will be traveling some distance before colliding with another molecule, right? So this is another molecule, it will collide. So for example, this is lambda 1, lambda 2, lambda 3, and dot 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 a lot. Okay, so what we do is that what is the mean free path is lambda I from I is equal to 1 to n, and then we divide by n. So this is the mean free path. Free path means that the mean path, the mean distance that a particle traverses before colliding with another particle. Okay. So what continuum hypothesis tells us that if this lambda, the lambda that is the mean free path, is very 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 small than delta x, then we can assume that this whole thing is a continuous thing. Okay, it does not we do not need to bother about the particles inside the domain. We can assume this material to be a continuous material. Okay, so this is the proper the initial assumption that we make. So there is something called a Knudsen number, which is nothing but a ratio of the mean free path divided by delta x. So it needs to be very very less than, for example, 0.01 to be for the continuum hypothesis to be valid. Okay. Okay, so let's now dive into the derivation part. So we assume that the whole this whole box is filled up with a continuous fluid, and what and this is just part of a large fluid body. For example, you have a pipe flow or a channel flow, that is fluid flow passing between two parallel plates infinitely long. Okay, so this cube is nothing but a small part of this. Okay, and at each control volume we solve these equations, and there will be numerous multiple millions, sometimes billions, such control volumes. So you have to solve for a million equation or billion equations for one problem to solve at each time step. Okay, so this is how complex things get when you finally go into solving this partial differential equation for any problems relevant to you. So we consider each this we divide this fluid. So this is a fluid, right? So we divide this fluid into numerous blocks or numerous this kind of cells, which we then use to solve the partial differential equations. So we solve these partial differential equations in these blocks. Okay. So what does conservation of mass tells us? It tells us uh, we have to see the change in, so the change in mass of the CB is nothing but the mass entering or leaving the control volume plus the mass generated inside the volume, right? You understand, right? So for example, if you have a box, uh, or for example, say you have a tank, water tank. Okay, there is an inlet and there is an outlet, and inside there is some mechanism, some imaginary mechanism from which water can be generated or can be destroyed. Okay, so at any moment of time, what can you tell? That the mass, the change of mass inside this volume will be a will be depending on the amount of mass that is leaving from this control volume and amount of mass that is entering, plus the amount of mass being generated or the amount of mass being destroyed inside the control volume. But we it's quite intuitive, and we generally know that mass cannot be generated or destroyed with ease in the scales that we are talking about. Okay, mass can be generated out of energy, and energy can be generated out of mass for nuclear processes, but we are not concentrated on that. We are concentrated on real life things that we generally see in our everyday life. Okay, so in generally what we see, we cannot create water out of thin air, right? We have to either condense the water vapor that is already there in the atmosphere, or else we cannot do that. So creation of mass and destruction of mass goes out of the picture. So what do we have? We only have the mass that is entering or leaving the control volume. Okay. Okay, so what will be the mass leaving a phase? Okay, so what is this change of mass of the CB? We can write it in mathematical terms. That is nothing but, yes, in a mathematical term, we can write it something like this. Okay, so for example, let me draw the coordinate system. This will be helpful, and the arrows pointing is the positive direction. Okay, so this is the positive x direction, this is the positive y direction, this is the positive z direction. Okay, now say this is delta x, this is delta y, and say this is delta z. Okay, so what will be the volume of this? What will be the volume of this control volume? So the volume is nothing but delta x times delta y times delta z, right? And how do we get the mass? So there is a property of this fluid called density, right? Which is nothing but the mass times volume. Okay, everyone with me? So what will be the mass now? So mass will be nothing but the volume times the density, or we get something like rho times delta x delta y delta z. Okay, I think this is quite simple, and will be you guys are familiar with this. Now, how do we mathematically write the rate of change of mass? Okay, so it is nothing but, you see, I have now used the partial derivative sign, right? Because the uh, mass will be a function of both space and time, right? So a function which is dependent on multiple variables, we cannot write it as a ordinary differential. We have to write it as a partial differential. Okay, so this comes out to be delta x delta y and delta z. Now in our case we have fixed this control volume. Okay, so the control volume is not moving and not expanding and not contracting. So what does it tell us? It tells us that these things will be constant, right? So what does this equation become now? This equation becomes times, okay, okay, so we have this term. Now the by the statement of conservation of mass, we can write this is equal to the mass entering or leaving the CV. All right. Now, what will be the mass entering or leaving the CV here? So, we have, for example, we have the values at the center of the control volume. Okay, let me just do a 1D demonstration that will be helpful. So, for example, this is the midpoint of the control volume, and we know the rho here. We know the velocity here, u, v, and w, or anything. But what will be the flux here? So for example, let this phase be the east phase. Okay. So what is the flux? Flux is the, okay, let's not flux. So flux is nothing but the mass per unit area per unit time. Okay. And if we multiply it by the area, for example, this is the area times the flux, we will get the mass flow rate. Okay, so what is the flux? So flux is nothing but rho times u at the phase E. Okay, because we have a continuously varying field, so the density is also a function of time, function of x, u, v, w. Both are all of the three are both function of space and time. Okay, so the density and the velocities here will not be same as in the boundary. So if you see, this is let us do a dimensionality reduction. So not dimensionality reduction, dimensional analysis. So this is kg per meter cube, and this is nothing but meter per second. Okay, so this comes out to be kg per meter square per second. So what does this term tell us? This is nothing but the flux. So it tells us the amount of mass crossing the boundary per unit time per unit area. Okay, and what will happen if we multiply this flux with the area? We get kg per meter square per second, and meter square is the area part, the dimension of the area. We get kg per second. Okay, so we will now get what is the flux here. So if you remember, at the center we have the rho and u, v and w. Now, and this is the delta x, and the distance from the center to this part is nothing but delta x by 2. Now we will use the Taylor series expansion. We know the flux here, right? Because we know these values. So, rho u at phase E is nothing but rho u at the center. So, let's call it C, or let's call it P. Okay, it's better. At P plus rho u do x delta x by 2. Here the separation is delta x by 2, right? So that's why we multiply with delta x by 2. Don't get confused with the Taylor series expansion here, where we multiply with delta x, because our separation was also delta x. But in this case our separation is delta x by 2, so that's why we multiply it with the delta x by 2. And as you remember, all the other terms we will neglect. You remember why we will neglect it? We will neglect it because delta x is very very small, very very small. So the delta x square and cube and to the power 4 terms becomes very very small and becomes negligible compared to these terms. Okay, so we'll only consider these terms. So you understand how we get the flux at this point, at this boundary. And to get the mass flow rate, we will nothing but multiply the area, which in our 3D case is nothing but delta y times delta z. Okay, now let's do a let's draw a diagram and show how things are. Delta x, delta y, delta z. This is the y direction, this is the x direction, this is the z direction, and the direction at which the arrow is pointing is the positive direction. Okay, if we move in this side is the positive direction, move in that side is negative direction. Okay, so what will be the flux here? Flux here will be rho u at this point plus rho x delta x by 2. Don't confuse with this dou sign and the delta sign. Okay, what will be the flux in this side? This is the same thing, but just the difference is that instead of multiplying with delta x by 2, we will multiply it with minus delta x by 2. Okay, because it is in the negative x direction, right? So this is the negative x direction, is the positive x direction. So that's why we have a negative sign here, and this will come out to be rho u plus delta x times minus of delta x by 2. Okay. And what about the flux here? It will be the same, but the only difference is that we will only consider the velocity that are perpendicular to this plane. Okay, because the velocities that are parallel to this plane, that is the u and w, does not result in any flux. Okay, so if you have a surface and the velocity is going this way and this way, so no flux is there across the boundary, no, right? So mass is not traveling across this boundary. So to get the mass that is traveling across the boundary, we need to get the velocity components which are normal to this plane. For example, in this plane, the u velocity is normal, so that's why we took the u. Okay, and in this plane it is the v velocity, so we'll take the v. So it will be rho v times dou rho v dou x delta y by 2, right? Because this is delta y and this distance is nothing but delta y by 2. Okay, and the flux that is leaving this boundary will be rho v times delta z, I'm sorry, delta y times minus delta y by 2. And similar thing we can do with the z direction. Okay, just a moment. Okay, all right. Okay, so let me just tidy it up a little bit. Uh, okay, another thing to notice is that I think I missed it out. So the velocity vector is in the positive x direction, right? So we consider it the u velocity will always point to the positive x direction unless and until if u is negative, then it will be reverse flow, and if u is positive, it will be in the positive x direction. So by convention we take it to be positive, so the direction of the flow is also in the positive x direction. Okay, so I'm sorry, I did a mistake there. And in the z direction it will be same thing. The z velocity, the w velocity will come from this side to the inside the plane, and again the z velocity will come out from that face towards the inside of the plane. Okay, so by looking at this image, what do we see? We see that in this control volume, this flux is entering the domain. This flux is entering the domain, while this flux and this flux is out of this domain, right? Here the fluxes are going out, pointing outwards. Okay, so if we now need to account for all these fluxes, we have a flux in the x direction which is coming inside the domain and one coming outside the domain. Okay, so the flux that is coming inside the domain will contribute to what? Increase in the mass, right? And this part where the flux is pointing outward and is going outside of the domain, this will cause a lowering of the mass, right? Because the mass is getting uh, exiting this domain using this flux. Okay. Now let's put all these things together and see how what we get. Okay. So initially we got the first part of the conservation of mass, that is the rate of change of mass per unit time times del x, del y, and del z is nothing but this in the x direction. Okay. Okay. So now in the x direction, let's account for the x direction first. So this part is coming in, right? So this will contribute towards increase in the mass. So this will have a positive sign. So rho u minus rho u by rho x times the x by 2. Okay. And this flux is going out, right? So this will be minus rho u minus delta x by 2. And to get the mass flow rate, we have to multiply it with the area, right? So here the area is what? This x phase area is delta z times delta y. Delta z times delta y. So here we have accounted for the x direction. Now let's do it for the y direction as well. It is nothing but rho v minus rho v by delta rho y by 2 minus rho v minus, and what will be the area? It is nothing but delta x times delta z. And we can do this is quite intuitive. We can do the same thing for the z direction. And the area is nothing but delta x delta y. Okay. So here you can see that few terms get cancelled out, and we add these two. Okay. So finally, what are we left with? We are left with we'll just add these two. This is divided by 2, so this the denominator will get cancelled, right? So we have minus rho u by rho x delta x, and we'll multiply this delta z delta y. You see where we are going. So rho v dou y dou x dou y dou z rho w dou z del x del y del z. Okay, and these terms are nothing but the volume, and it is there in with all terms, so we can just cancel these terms, and we can finally take these whole things to the left hand side and assemble the equation to get the final mass conservation equation. Okay, so this is the proper um, equation for conservation of mass, where we have variable density, and these are the two parts actually. This is the temporal part and this is the convective part. Okay, and if we see that if we take rho is constant, we can just get rid of this first term, and we can bring out the rho from inside the derivative, and we can just get a simple dou u by dou x plus dou v by dou y plus dou w by dou z is equal to 0, right? And we can also write it as the divergence of the velocity vector. Okay, so if you remember from your vector calculus, so divergence is nothing but dou by dou x I cap plus dou by dou y j cap plus dou by dou z k cap, and your u vector is nothing but uy cap plus vj cap plus w k cap. Okay, so this is what we get finally as our conservation of mass. Okay, and this is for compressible flows, and this is with the assumption of incompressibility. Okay, so till now do you guys have any doubts? Please feel free to unmute yourself and ask me questions. Anybody? Please don't be shy, and you can ask me any question if you want. Okay, sounds good. So there is a another way that we can get these equations. Okay, so there are actually a lot of other ways you can derive it, but this is I find it the most intuitive and better way to derive the equation in such a manner. Okay, so also do you guys know the concept of the material derivative or the substantial derivative? Okay, then so what a material derivative is, borrows the concept from, not borrows the concept, it comes out of the concept of the approach of fluid mechanics. Means there are different approaches in the fluid mechanics. One is the Eulerian approach, and one is the Lagrangian approach. Okay, so the Lagrangian approach, what it does, what it does is that it follows the fluid particle. It follows the fluid particle along its path, and it notices the change of this particle. For example, the U particle, V particle, W particle, density particle, which is a function of time and as well as a function of space. Okay, so what it does is that it tracks the particle, and using the information, the property changes of this particle, of this particular particle, it gets the information about the fluid flow. Okay, so in this manner, what you have to do is that you have to you have to follow a lot of particles to get the picture, the macroscopic picture of what is going on. And another approach is the Eulerian approach. In this approach, what we do is that we don't follow the particle. Our reference frame becomes stationary, and particles can freely travel from here to there, whatever they wish. And we are only considered uh, about the closed volume that we are focusing on. So we will not be considering all the fluid particles that are entering or leaving, but we will only consider the things that goes in and comes out. Okay. In that manner, what we can do is that we can simplify our problem from tracking millions and trillions, even billions of particles to one single control volume, and only focusing on the boundaries, what goes on, what comes out, and all that. And using those information that we get from the boundaries, then we can construct a view of construct an opinion of how the fluid inside that domain is behaving. Okay, so what the material derivative does, material derivative is nothing but the rate of change of a property. It is denoted as capital D, the rate of change of a property with time when you are following a particle. Okay, so following a particle is quite intuitive, but when we go to the Eulerian approach, it becomes conceptually difficult. So what the material derivative does is that when we have the limit of delta t and delta x very small, okay, very small, then we can at a particular instant, at a particular control volume, we can equate these, both of these two. All right, so we can, this material derivative can be equated with the control volume approach. Okay, you will see it in I will show it how it comes up. So for example, if you have a, for example, a continuous field variable phi, which is a function of x, that is the position and time both. Okay, so if you want to get the change of the change of phi with respect to time, or we can write it something like this, we get so we have a temporal derivative, then we also have a spatial derivative, right? But here in this case, when we are following a particle, the x and t are not independent. Okay, the x and t are not independent. What does it mean? It means that the x and t are related by a concept called the velocity. Okay, so the